Alright, so if we are writing the formula for ammonium nitrate, ammonium is one of our polyatomic ions. It's the only cation that I asked you to memorize, and then nitrate is another polyatomic. So again, there's nothing wrong with giving yourself little notes out to the side of how to put them together. So if I have NH4, that has a +1 charge, and nitrate is NO3 with a -1 charge. When you crisscross those, the 1 would come down and the 1 would come down, but we don't write the subscript 1. And so since you don't need a subscript on either one of those, you don't need parentheses on either one of those. So it would just become NH4NO3. So I have 1 ammonium and 1 nitrate. And then this decomposes. This will become important when we talk about types of reactions in a minute. But ammonium nitrate decomposes, which means it breaks down to form dinitrogen monoxide and water. So dinitrogen monoxide is a covalent compound that is nitrogen and oxygen. Mono means 1, so there's only 1 oxygen. Di means 2, so there's 2 nitrogens. So N2O plus water, which is just H2O. So we've learned several ways to name water. Sometimes you'll see it as a funky name, sometimes you'll see it as just water. But yeah, hopefully you all know that it's H2O at this point. Then, when we list our reactants and products underneath the arrow here, what's important to note is that we do have 2 polyatomic ions on the reactant side, but the rule that we learned on the previous page was that polyatomics that are unchanged on both sides count as a single unit. So since I don't have those same polyatomic ions on both sides of my equation, there's no ammonium on this side, there is no nitrate on this side, I can't list them as ammonium and nitrate like as a whole. So I have to actually break them down into the individual atoms that make them up. Because if I were, so if you tried this, I'm going to do it in pencil just so you can see what I'm talking about. If I were to list NH4, and then I say, okay, I have 1 NH4 on this side, but then I count how many NH4s I have on that side, and it'd be 0, that doesn't make any sense, and you're not able to balance with that. There's nothing I can multiply that by to make it equal. So I'm going to just list out the actual elements to balance this one out. So I'm going to list nitrogen, and then I'm going to list hydrogen, and then I'm going to list oxygen. So I have a nitrogen, hydrogen, another nitrogen, oxygen, nitrogen, oxygen. So everything is covered. So then I count them, and I have to add them together similar to how I did in the last example. So how many total nitrogen atoms are on my reactant side? 2. So 2 nitrogen atoms. I have 4 hydrogen atoms. And how many oxygen atoms? 3. Nolan, are you good? Okay. On my product side, I have 2 nitrogen atoms. I have 2 hydrogen atoms. And I have 2 oxygen atoms. So note that your oxygen atoms are in 2 different places. So 1, 2. So you're taking the total number of each atom on each side of the equation. I'm going to switch pens so it's a little darker. So my nitrogens are already balanced just to start, but my hydrogens are not. So to change this, what coefficient would help me, and where should I put it? Okay, a 2 in front of water, so a 2 in front of H2O. 2 times 2 hydrogens gives me 4 hydrogens. And then 2 times 1 oxygen gives me 3 oxygens that come from water, plus I have the 1 oxygen still, sorry, not 3, I don't know why I said that, 2, plus the 1 from N2O. So 2 plus 1 gives me 3. So there are a total of 3 oxygen atoms on my entire product side, which is equal to the number of oxygen atoms on my reactant side, so we are already balanced. Yes. And then in the blanks, if you didn't have to change anything, so once you're all the way balanced, put 1s as your coefficients, just to make sure that you know them. Alright, then the next example, letter F, is C6H6 plus O2 yields CO2 plus H2O. So this is combustion of a hydrocarbon. We'll talk about this one as well later on. Combustion is when anything combines with oxygen, and then a hydrocarbon is any compound that contains hydrogen and carbon. So combustion of a hydrocarbon will always yield carbon dioxide and water. So you'll get used to seeing something like this. These cases are often pretty tricky to balance because the numbers that you get in your hydrocarbons can be kind of bizarre. They can give you really weird coefficients. So don't be weirded out if you get funky numbers that you're multiplying by. So when I put these together, I'm going to list carbon as my first element, hydrogen as my second element, and then oxygen as my third element. On my reactant side, I have 6 carbon atoms, I have 6 hydrogen atoms, and 2 oxygen atoms. And on my product side, I have 1 carbon atom, I have 2 hydrogen atoms, and I have 1, 2, 3 oxygen atoms. This is also why one of our tips was to leave hydrogen and oxygen last when you're balancing, because if they occur more than once or more than twice even in an equation, and you balance them to start, you might end up messing something else up later. So leaving them till the end is generally pretty helpful. So first, I would just start with balancing my carbon. I have 6 carbons on my reactant side, so I want to get 6 carbons on my product side if possible. So what coefficient would help me? A 6 where? A 6 in front of CO2, so 6 times 1 carbon gives me 6 carbons, and then 6 times 2 oxygen atoms gives me how many oxygens? I get 12 oxygen atoms from carbon dioxide, plus I have 1 oxygen atom from H2O. So how many? 13. So again, this is why I keep emphasizing that down here, when you're tallying them up, you're not doing any math down here. We didn't just multiply 6 times 3 because that would have given me 18. That's completely different than the number that I'm actually showing. I didn't change the coefficient on both compounds. I have oxygen in 2 places, so you only needed to change the multiply out on one side, and you just add that one. And then if you're going to forget what this means, then cross it out so it doesn't confuse you. So now my carbons are balanced and my hydrogens are not balanced. So what do I need now? A coefficient of 3 on H2O. So 3 times 2 hydrogens gives me 6 hydrogens. 3 times 1 oxygen gives me 3 oxygens from H2O, plus the 12 that I already had from 6 CO2. So I already had 12 oxygens from here, plus I'm adding 3 more. So now, instead of 13 oxygen atoms, I have 15. So again, this changes only as a result of your coefficients. I'm not multiplying this total count by 3, because that total count came from adding all these together, and I only changed the coefficient on that compound during that last step. So a rule that we kind of glossed over on the previous page was that all of your coefficients need to be whole numbers. So we did list that it's the lowest whole number ratio. So you cannot actually have a coefficient that's not a whole number. However, temporarily in this kind of case, what I think is the easiest to do is use whatever it takes to make them equal each other and then get rid of the number that's not a whole number. So what I mean by that is, wouldn't it be perfect if my carbons are balanced, my hydrogens are balanced, my oxygens are not balanced? I have 2 on one side and 15 on the other. And this 2 oxygens is coming from O2, so I know for sure that no matter what coefficient I put in front of this, I'm going to get an even number on my reactant side. There's no possible way that I can multiply this by a whole number and have it equal 15. But if it didn't have to be a whole number, what number could I put here to get it to equal 15? I think I heard it. 7.5. So I'm going to cheat it just a little. So 7.5, knowing that I cannot leave it this way. So 7.5 times 2 oxygens will give me 15 oxygens, and now everything is balanced. So if everything is balanced, then what goes in this blank? 1. So we can leave it there temporarily. However, I cannot keep it that way. So to get rid of the 0.5, I can multiply this entire thing by 2, and then just double all of my coefficients. So instead of this being 1, it's going to be, what? 2. Instead of this being 7.5, it's going to be 15. Instead of this being 6, it's going to be 12. And then instead of this being 3, it's going to be 6. So 2, 15, 12, and 6 are the coefficients that should keep this balanced. If everything got doubled, then really all of these numbers should be doubled as well, but just to make sure that I didn't mess something up, you need to go back and double check. So if I do 2 times 6 carbons, how many total carbons are on my reactant side? So 12. 2 times 6 hydrogens, also 12. 15 times 2 oxygens, 30. So then I do 12 times 1 carbon gives me 12 carbons. 12 times 2 oxygens gives me how many from carbon dioxide? So 24 oxygens from CO2, plus I have 6 times 1 oxygen gives me 6, so I have a total of 30 oxygens on my product side, and then hydrogen is 6 times 2, so 12. Is everything still balanced? Okay, so this is a special case where it's difficult balancing, or it has the potential to be difficult balancing. So I find this trick really useful. Some of you will get so used to seeing it that you'll just know that it's 15 right off the bat. But double check at the end. People make silly mistakes here. So you'll start to recognize it's when you're combining a hydrocarbon with oxygen, or we call that combustion of a hydrocarbon. You have a question? Yes. So if you are able to reduce it, thank you for bringing that up. A lot of times with these cases, you will also end up with something you can reduce. So just double check that you can reduce it. I have a 2, a 15, a 12, and a 6. Can those all be reduced by the same number? No. So there's nothing that I can reduce this by, so this is already in the lowest possible ratio. So the answer is yes, you would end up reducing if you're able to, but in this case, we can't reduce it. So lowest whole number ratio. Alright, last balancing one. This is just learning another trick that if you break water into hydrogen and hydroxide, it's sometimes easier to count. So if I put underneath this, I'm going to just change the H2O to H, I'll write it up here, HOH. And then when you count this, you are going to count them separately. So your hydrogens are not going to be double counted. You're going to count the hydroxides and then hydrogens that are not part of hydroxide. So I would list lithium as my first one. The next one would be just hydrogen, and then the third one is hydroxide. And then lithium, hydroxide, and hydrogen. So the H's that are part of hydroxide don't count in the hydrogen tally as well. So next to lithium, I have 1 lithium, I have 1 hydrogen, and I have 1 hydroxide. On my product side, I have 1 lithium, I have 2 hydrogens, and I have 1 hydroxide. This makes it easier because then you don't have to think, okay, I have 2 and 1, and you don't have to add them up and make it equal 3. You just count hydroxide as its own thing, so you count that as like being unchanged on both sides, so hydrogen and hydroxide. My lithiums are already balanced, my hydrogens are not, so I would put a coefficient of 2 in front of HOH or in front of water. So 2 times 1 hydrogen gives me 2 hydrogens. 2 times 1 hydroxide gives me 2 hydroxides. So then my hydrogens are balanced, but now my hydroxides are not. So I need what coefficient? To where? Good, in front of lithium hydroxide. So 2 LiOH, 2 times 1 lithium gives me 2. And 2 times 1 hydroxide gives me 2. And then last coefficient, easy one, goes in front of who? Lithium. So 2 lithiums, 2 times 1 makes that count 2. So 2, 2, 2. Everyone is balanced. And then in my last blank, since I didn't have to change anything, what do I put there? 1. Perfect.